All right, it's Tuesday of week three here. Um, I'm going to talk a little bit there. I had a couple of students asked me about assignment two, so we'll talk a little bit about that. And then we'll kind of do a normal Tuesday activity. We'll go through the new material here. We're jumping into more details on language definition, talk in much more detail about scanning and parsing and how that works this week. And then next week, we get a little more theoretical and we look at automata that are used or related to this sort of stuff. This gets us into the area of computational theory. Later on in the course, we'll look at this type of automata and tweak it a little bit to create what is called a Turing machine, and then use that to do a lot of proofs about what computers can do here. But at this point, we will look at it much more in the applied context. How do we use it with our grammars for defining a language here? One thing I would like you to do is this course feedback for week three. This is just a survey that you can fill out. Just make some suggestions. Again, this is a brand new course. I'm developing this as we go here. And so I'm looking for some feedback on how you like the course, what you like about the use of AI in the course, what you'd like to, if you had one thing you could change or get rid of in the course, what would it be? There's something you'd want to keep or you like in the course, what is that? So put some of that in there. It's just a short, I think it's just 4 questions here. So let's look back at last week. We were talking about Bacchus-Naur form, and the assignment was this larger language, which is called Ren. It's still a very simplified language, a little more complicated language here. And then your assignments were to work with this to do a couple things. One would be to generate a program with this language here, starting with the program thing. So again, I'm gonna maybe move this over. Here's our language. What I did, I found out that even in the PDF, I couldn't copy this text very well. I like to copy this text, so I just pasted an image of it into AI and have it generate some text. So I'm just going to use that. I might move that over here for next time we do this. But again, what we're doing, we start with a program tag, our top level tag, and then we apply these rules. And again, there's only one rule that does a program, and that's this program equals the word program, and identifier is in a block here for this. So we put that in here, and then so our new kind of code now is this. Run the word. We have the word program. We have the identifier and a block, and is and then a block. And again, we can then look and do a rule for either of these. We want to eventually have this all terminal ideas. So we can look at identifier or a block. It doesn't really matter which one we substitute first. Let's do identifier because I like to start at the left here. So I look for a rule that has an identifier here, and here's an identifier for this. And so there can be multiple rules here. So an identifier can be an identifier and then a letter. So I'm going to actually do that next. So now what do we have? We have this. But now where the identifier is, we're just going to do this part. We're going to replace identifier with an identifier and a letter. So now we have our program can be our program identifier and then the letter. Let's make this just a 2-word program name. So I could keep doing this and adding letters here, but I can also just apply this rule. Identifier is a letter. So now I have my program is now I'm taking the identifier and swapping that with the letter. So now a program is just a letter is, and a block. And again, now I can substitute these letters in here. I'm not maybe going to grab all these, but I'll do these rules. So I'll do a letter is one of the letters. So now I've got this as my program. So for one of the letters, I'm just going to choose, again, the OR letter. So let's put a B letter in there. And again, I can do the same thing. And again, maybe I could write it more like this then. Oops. Letter, let's do an E. So far my program is program B is, and then I need a block. Again, it's just applying these rules to make a program. So like, what is a block over here? So I can look at a block. It is this. I'd apply that rule next. So. Where the block is, I do this. I'm going to maybe put this on some separate lines to spread it out a little bit. So this is a program that doesn't use braces, but has begin and statements in it for that. And again, I would keep applying this stuff to build out this statement here. Do you guys understand that? Does that make sense? That, I mean, we're able to apply this table and work through this stuff fine? So, how about this last thing? Can you convert this program that's in Java into a Wren program? That's a little harder to do. It's sometimes harder to see the full syntax here. But again, I think once you work through this, you should kind of see that, right? So the idea is, what does a program, what's the minimum program look like here, and what's the format for this? And so we kind of begin to see that we always, well, let's just take this as our program to start with. We always say program and then the name of the program. So we could put the same name in here. Weekly calculator is the declaration sequence. What is the declaration sequence? It can be an empty set, or it could be a list of variables here. Variable, the type, variable list, and then the type for this. The type is integer or Boolean for that. So we have the var. So again, we create our var is, and then let's put this down here. So we declare all of our variables. We say var, and then we have our variable list here. So we would do our, like, hours is an int. And by looking over here, I can kind of try to build out, again, with what this program is. I know a declaration for one variable is the word var, a variable list, and then a colon and a type here. And a variable list is just variables separated by commas for this. And then the only two types I have is int and Boolean here for this. According to this. So I can say hours, integer, I could say, and I can have another variable here, and I don't see a semicolon at this. Or I guess, where's my declaration here? I've got a declaration sequence. Yeah, so I just say declaration, declaration. I don't see commas in between them or anything like that. So I think I think they're just like this, hours calling integer. And again, I'm gonna put them on the separate line and then do my variables pay rate. Now, one problem with this is that in Java, we have doubles, and here we don't seem to have doubles. We have integer and Boolean. So you could do two options here. You could just say, oh, I'm going to use the only numeric type I have and say integer. I'd be fine with that. Or you could do, make it just say, oh, well, let's say we had a double there and do it as double. And again, you could also say, you can have separate lines, or you can put them on the same line, something like that. So we have our variable declarations, and then we have our commands. And again, we'd want to look through this if statement and look at how do we declare an if statement here. So here we'd say if some Boolean expression, then a command sequence, and then an end if. So we'd want to do it that way. So instead of this way where we have the braces for this, or else like here's our else, I guess we'd want to use that one. So the idea is that can you understand this language enough, given this BNF syntax, to write a program, a simple program in that language? So were you able to do that? How was that this week? I think that's certainly the more challenging of the questions here. Online students were able to work on that? Okay, I'm going to leave that be then. Then let's jump into chapter 3. So last week I was able to find a nice textbook chapter that goes over this, the material we wanted. This week I wasn't able so much, so I've used AI to generate some of the descriptions I wanted here. I'm using stuff from two well-known textbooks, Sebasta, Concepts of Programming Language. Chapter 4 is on lexical analysis here, and Scott, sections 2.2 and 2.3 on scanning and parsing, which we'll be looking at here. Again, I've been looking through these, and these provide some good examples, but they also have stuff that I don't like so much. So like Sebasta is going to go talk about, this, what we call lexical analysis or scanning, and creating tokens, and how we will take things like the equal sign and say that's an assignment operator, and this is an identifier and stuff like that, and tries to work through, but doesn't have what I say a great example. Yeah, it has this example showing a transition statement where you start and you'd try to figure out if an operator is an identifier or an arithmetic expression or unknown here, and works through that. It's okay, but not great. Scott does a similar stuff here. Where we'll walk you through, again, this idea of scanning here, and talks about different rules for scanning, and then goes through this example. And we actually look through this example more here, and how we can look at an assignment. And again, this flow. And we'll talk about these finite state machines some. There are also a number of places where faculty have put their own lecture notes, largely almost textbooks here out there. So again, this is a textbook by Margaret Fleck. Yeah, from again, it's quite old, but it's not bad. Again, talking about this, these state machines and finite automata, which we'll cover actually next week. It goes a lot into state machines and finite automata here and stuff with that. But also then talks about some of these. Let's see if I can get. Well, actually, it doesn't. Yeah, it talks about context-free grammars is what we're working on here. So again, I didn't find a good chapter that covers what I want. So I'm just going to go through with AI what we want here. So last week we talked a little bit about context-free grammars here. We really talked, Bacchus-Naur form is really basically used to generate, can be used to generate context-free grammars here. Now, a lot of places will specify a very mathematical definition of this. So a context-free grammar is a four-tuple here. G, our grammar, is made up of V, sigma, R, and F's, where V is a finite set of variables. So those are our non-terminal variables, things like expression and statement. And again, we often see these in these tags, greater than, less than tags here. And again, that comes right from our grammars here. We have a set of sigmas is our set of terminals, file tokens like letters, numbers, digits, stuff like that here. So the actual terminal characters. Then we have a set of rules here, and the rules are generally what they call production rules, where we have a side B generating a side W. B is a subset of V. W is a subset of V and sigma. So it's a terminal or a non-terminal here. And then we need a start variable. So at least one of the non-terminals has to be marked as a starting variable for that. So again, we can create a very mathematical definition, and some textbooks spend a lot of time on the mathematical definitions of this. But again, we can walk through what these are. So here's an example of this. But again, I like to think of it more in terms of B and F stuff. So we have a set of non-terminal symbols. We have a set of terminal symbols. We have a set of production rules. And then we have a start symbol for that. And that's what we worked with a lot last week was, specifying. Sometimes the start symbol wasn't clearly implied, but it's out there. So. Now, one of the things that's dealt with a lot, and we'll talk about more than I think we should, is ambiguity with these. And it is possible to generate Bacchus-Naur, these grammars or these context-free grammars that are ambiguous, meaning you can generate the same string multiple ways for this. And here's an example here. So we have our variables are, we have and again, this isn't using the bracket technology, but again, we're using a sentence, a noun predicate, and an adjective, and our different, and think of just words, and, eggs, ham, pencil, green, cold, tasty, etc. And then our rules are non-predicate, we could say non-predicate or NP and NP. We can say NP can be an adjective in NP, and NP can be an or a noun could be eggs, ham, pencil. Adjectives could be green, cold, tasty, or whatever. So if we start with S here, and we want to generate green, eggs, and ham, There's two, and again, this kind of gets to the ambiguity in English language. When you say green eggs and ham, are the eggs green or are the ham and the eggs green? So when you ever think green eggs and ham, is ours the ham green? That's the question. Is the ham green or is it just the eggs there for this? So can you remember back to Dr. Seuss? Do you remember how Dr. Seuss, well, who's the illustrator for Dr. Seuss? Was the ham green or was it just the eggs? Just the eggs, you thinking? Yeah. So, so again, what this is showing is there's two ways of parsing this. So, Allie's out there Googling green eggs and ham and bringing up the pictures of it and trying to figure out if was the ham green in green eggs and ham. Okay, there's two ways of parsing this. So again, it just depends on what order we apply the rules. And again, back at this example, you can remember I said, like this program identifiers block, I could do the identifier first or the block first. I could substitute a rule for either one, and it didn't matter. I said, well, if it's a unambiguous grammar, it doesn't matter. But if it's an ambiguous grammar, it could matter somewhat. So again, we can take S and we can break S down to now NP and NP there. Or, so we could apply this rule, or we could take S. So S is going to be, I guess I don't even show what S is here. But S can be a adjective and an NP here, an adjective and an NP for this. So we could do either this one or this one for this. And again, and then we could take our NP and say it's an adjective and an NP, and then we have the and then this NP is just a noun and here. So we end up with green eggs. And so the green and the eggs are tied together on the parse tree. So green is only fitting the eggs because they're only on that part of our parse tree. And we have ham over by itself. Or we could parse it this way, where we pull out the adjective first, and then we have eggs and ham as a complex noun predicate here, an NP. And so we're saying green eggs and ham. So both the eggs and ham are here. Now, this is talk about ambiguity, but we'll talk a fair amount of what we call deterministic and non-deterministic here. Is there only one way to generate sentences, to parse sentences here? So in English, often there are multiple ways to parse things so that you can take the same sentence and interpret it different ways for this. And a computer, we certainly don't want that. So we're going to want, so this is called an ambiguity, or we'll see determinism. We'll talk about non-determinist or deterministic stuff. And we'll deal more with that next week when we get to what we call automata and kind of formalizing that part, this parse tree stuff. So questions on this example? Okay, so we're going to look at two things here, scanning and parsing. It's kind of two separate operations. So today we're largely going to talk about scanning, and on Thursday we're going to deal more with parsing. So scanning or a scanner and sometimes it's called a lexical analyzer, or we'll abbreviate that to a lexer, L-E-X-E-R here and for this. And it will be a way we're going to take our characters and convert them into tokens here. Like I mentioned before, this is actually very similar to what AI is doing these days, where it is taking your prompt and converting your prompt into tokens. And in fact, I was looking and putting a quote together for an AI proposal, and all the AIs, their price is the price per tokens or price per million tokens is what they're doing. So how much does it cost to send a million tokens or get a million tokens? So they don't deal with words, they deal with tokens here. Generally, it's about a word per token, or you often need a couple. Sometimes you need a couple words for, so you might get 4 tokens for every 3 words, sort of stuff here. Here we're doing much more at the character level. Well, we're putting together characters and trying to create tokens from them here. So a token would be like that's a number, or that's an operator here, that's a keyword, or that's an identifier when we're going through our language. And this week we're gonna talk about finite state machines, because I think you're probably more familiar with finite state machines. Next week we'll start calling them something different. We'll call them finite automata. For that. And in our minds, finite automata and finite state machines are basically the same. We'll transition to that language because from that we'll build what are called push-down automata, which are a little more complicated versions of this here. So how do you create a scanner here? So one is you can manually construct one by what you know of the language here. Create a finite state machine for it. And we'll kind of look at that today. Another thing you can deal with are regular expressions. I've been trying to figure out how much to go into regular expressions. So what do you know about regular expressions? Here. I run into them lots of places. I'm over time they're like these expressions that try to denote strings, particularly like if you're doing a search or something like that. Yeah, let me bring up. For a to verify and email address that must start with a character. This is like a regular expression. Have you ever seen things like this? So I mean, like this is saying it has to start with the first thing has to be a character, lowercase a through z or uppercase a to z. So that's kind of the symbol, or the takes place of a single character. And then it can be followed by characters or numbers or a couple special characters like a period, a dot, or an underscore for this. And then it has to have the @ symbol, and then it has to have some, again, characters, and then it needs a period, and then more characters for this stuff. So, and then these are examples that would work and wouldn't work for that. Have you seen regular expressions? So yeah, right? So you have like when you're doing search things, even just the using, I guess, the brackets and stars or something like that. So you may have seen, we'll see them. I'm not going to be teaching you a lot about regular expressions. They can get quite complicated here, but you'll see them mentioned a number of places with grammars and languages here. I'm trying to think of like SQL. I think with SQL, you can specify some regular expressions in the select statements for that. Certainly any place else where you're doing a search, you can specify regular expressions somewhere. Okay, so you can build things up with regular expressions and here. Now, there are a number of tools to do this automatically. 2 common ones on come from Unix. Lex and Flex, and Antler is another one, but Lex and Flex, I think, are more live. They're older, so that's why I know them better, I guess. So these are tools that will generate your lecture automatically. Although nowadays we'll see our AI can also just generate code to do this automatically also. Sometimes we'll see these state transition diagrams or finite state machines will do this stuff. So let's look at a finite state machine and how it would work here. So again, finite state machines are usually shown with a state transition diagram here. So you have these states, 1, 2, 3, 4, 5. Each numbered thing is a state here. And then as we get input into our state machine, we read each input character, we can transition to another state here. And all these, there's this implied error state where if there isn't if we see a symbol and it's not, we don't have a transition for it, that should generate an error for this. So here's our simple state transition diagram for this. So how would we, what could we do? What are we trying to parse? So let's say we're trying to parse a number here. So like we are trying to parse, let's say, so let's just say, hey, 2016 up here. That's a number. So again, we start here. We're going to see the 2, which is a digit. So we don't see this, we don't see this, we don't see a colon, we don't see a period, we see a digit. So if we see a digit, we go, oh, this is going to be a number. So we go down in here. And again, we see the 0, that's another digit. We're still in state 14. We see a 1, that's another digit. That's here, we're still in state 14. 6 is another digit. We're down here. And then we see a friend, and that's maybe a different thing. So up here. So then we're going to stop and say, we're saying this is a number. Another thing is we could see a decimal, so we should see a couple digits and then a decimal and a couple other digits, and we can also say this, it could be a number for this. And again, in some languages, we'd have like this would be an integer and this would be maybe a double idea. We can also start maybe with a period. We could see a period first and then a digit, and then we'd say that's also a number for this. So this just tries to show the transitions as we see objects, and as we see characters, and we're trying to parse a statement for this. So let's build a longer example of that. So again, we are trying to parse our characters, sometimes called lexemes, into tokens here. So our tokens will be identifiers, so like total or X, numbers like 3.14, operators like plus, the star operator for multiplication, parentheses, and white space possibly. And again, we can specify regular expressions for each of these things. So like a number starts with a digit and has one or more digits, followed by a period and one or more other digits for this. Now in this case, I'm trying to remember what, with a number, does the number have to, can a number start with a period? Can it have just a dot? Can you just say dot 47 or do you have to say 0.47 to do a number? And does it have to have if you have a dot, and does it have to have a period after it here for that? So, and how do you set that up? So like here, this is actually set up so that you don't have to have a period. That's what this question mark is makes this optional. But if you have a period, you do have to have at least one decimal, one number after it. here. So you can say 2.0, but you can't say 2 point. That wouldn't be a legal number. If I'm remembering this regular expression. I always forget with regular expressions what's the period of the, all right, what's the plus? Is that 1 or more, 0 or more? What's the question mark here? Stuff like that. So I often have to look these up. But here's the regular expressions. Here's our grammar. This is what we're more used to doing here. So an expression is a term plus or minus in another term. A term is a factor multiplied or divided in another factor. And a factor is a number or an identifier or an expression in parentheses here. And a number is a digit plus a period on other digits. And again, this is actually BNF format. So this little question mark says that this period and other digits are optional for this. An identifier is a letter followed by multiple letters and digits. And here's our digits, here's our letters for this. So that's kind of our grammar setup now. I think I'm trying to look at this grammar. One thing I see with AIs is sometimes I forget rules in here. So I'm looking at this and saying, well, oh yeah. So what again? Because I was thinking Bach-Snauer format, but this is actually extended Bach-Snauer format. So the expression is a term, and then this means and 1, 0 or more of this. So you can have a term, and then you can optionally have a plus and a minus in another term. So that's the format it's using here. So you can have an expression that's just a term by itself. A term can just be a factor can just be a number. So an expression can just be a number by itself. Yeah. But from either this or from this, we can kind of create a transition table for this stuff that we would draw this out as. So we could look at this transition table where we start at state 0, the start state, and if we see a letter here, we would go to state 1. If we see a digit, we go to state 2. If we say a C plus minus any of the operators, we go to state 3, state 4, or state back. If we see a space, we go back to state 0. So again, that's kind of showing this here. If we see one of these, again, this is a different numbering system, but this is same sort of idea. So we could draw a diagram for this stuff that would try to specify how we go. So again, if we see a letter, we start at 0. If we see a letter, we go to state 1. We see another, so now we're in state 1 here. If we see another letter, we go to state 1 again, and we see another letter, we keep staying. So as long as we see letters, that's fine here. And then when we're done, if we see like something else, a digit or a space or something, we accept that and we say that's an identifier here. If we see a digit, we go to state 2, and then we see more digits, we'll stay at state 2 for this, and we'll say that's a number for this. An operator, we see an operator, and then anything after the operator, we'll just call it operator, because operator, in this case, operator is just a single character for this. So this is a very basic table. In this table, identifiers can only be letters. They can't be letters and numbers for this. So because, again, if we see a letter, we go to state, we start 0, we see a letter, then we're going to state 1. So now we're in state 1, and we see another letter, we can go to state 1. But if we see a digit, then we're accepting it and saying, oh, that's the end of that identifier there. If we wanted an identifier to be made up of letters and digits, we'd have to put like, say this stays in state 1 here for this. Okay, so I'm going to want you to dig in some more to this with some prompts. Now, I'm asking you, remember, I'm asking you for your feedback on what we should be changing in this course, but I'm also changing something this week in this course based by what I've seen so far and what I want you to do. We were doing QQTP, question, quotation, and a talking point here, but I really want, I want to see you, I mean, the idea of these prompts is that you can be asking the AI, I give you some initial questions, you can feed those to an AI, but then you can ask AI to, like, if there's something you don't understand, ask AI to tell me more about that. And you can really customize this learning to what you know and what you don't know, and to fill in all the blanks. And what you're interested in, you can ask AI. So to push you more in that direction, I'm having every week now you a question and a quotation from the prompts, but also a student prompt. So some prompt that wasn't in the list that you added to this. So I wanted you to provide one of your own prompts, and then what was the response from AI for that. So this week we want a question, quotation, and a student prompt for this. And again, we'll have this due on Thursday. Maybe, I never know when I should have the due date for this, because the whole thing isn't due until Sunday. But again, we want to be able to analyze these in class. So I'm going to put an initial due date for a class on Thursday. And then on Thursday, I actually switch this. So I want the initial QQTP stuff, and then the interactions you have until the following Sunday to work on. Okay, so why don't you bring up this Unit 3 prompt document, make a copy of that. And pick your favorite AI. So I don't know what's on your social media. Oh, did someone say anything online?
Yes, I think you put 2024 as the due date.
Oh, I put, so you're already late. Let's see. Yeah, I did. Okay. It should be the 18th, right? That's this Thursday. No, that's, I don't know where this got set at. Okay, we want this to be January 30th. Okay. Sound good. Okay. Yeah, because this is February 2nd. That looks right. So I don't know what your social media feeds are, but mine is all about the new AI system from China, this DeepSeek. Have you heard of DeepSeek?
I heard about it.
I think it cost me $10,000 this weekend just in lost stock.
A lot of stocks went down.
But it cost me $10,000 and just because it made the other stock prices just crash. But it's the new, right?
Yeah.
It's new from China, a company, a quantitative analysis company based in China. And it's very good, and it was free, but so many people using it. I don't know. I couldn't get access to it this morning. So do large-scale malicious attacks on DeepSeek servers. Registration may be busy. Please wait and try again. Registered users can log in normally. So I've been just logging in with my Google account, and this morning it wasn't working. Oh, there it is. Okay. So I added that with our prompts here, so you can figure out which one you want to try here. Okay, so why don't you try to go through those. Remember, specify the opening prompt here, and then work through these, and we'll talk a little bit about them in a sec. I mean, as we go through. So start working on those. Okay, I'm going to pause the recording here for a little bit. All right, let's break in here a little bit, see how we're doing. So hopefully you've been looking at, the first part is on determinism, and we looked at that ambiguity, but the more proper term for it is generally deterministic or non-deterministic here. And again, so you should be seeing stuff, and again, some of this will be due more next week. Like here saying a deterministic context-free language, a DCFL, is a subset of context-free languages that can be recognized by a deterministic push-down automata. And that's what we'll be learning more about deterministic push-down automatas and this whole idea of automata next week. They're very closely related to finite state machines there. So we'll actually start off with finite state machines and convert them to push down automata by adding a couple of features here. So again, this means every input string there's only one unique way of processing it or parsing it here. And we'll talk, this is going to impact us a lot with parsing here. There's only going to be one with deterministic finite automata, there's only going to be one legal way of parsing that set of symbols into a meaning for this here. Now, remember, we want you to be at least do one of your own prompts here. So like here, I was, just wondering, let's see, what did I type in here as my own prompt? So can we prove, again, this isn't this, I was just wondering, like, okay, so if we have a context-free grammar, how do we tell if it's deterministic? Can we prove that a context-free grammar is deterministic? Are there tests for determinism here? So this kind of walks through this. Deterministic, every non-terminal A is followed by conditions that hold the first set of conditions. If a non-terminal A has multiple production rules, they must be disjoint. You can't have, it can't be some overlap between them here. And we have to watch empty production rules for this stuff. So again, it walks through some of the conditions that you can set up for the rules here. When we're working on this. So, and again, ambiguous means that we're non-deterministic for this. So, okay, so yeah, remember, you're supposed to find at least one prompt that you put in that you want to share. Did that determinism stuff make some sense to you? Questions on that? The next thing we're going to look at is scanners. And again, we'll be working with this a lot on some on Thursday, especially table-driven scanners for this. The scanner is usually done with a finite state machine, but which can be kind of described with a table of states if we go through. So see how one of the problems I have with AI is that it's not good at creating diagrams. So I'm really interested if someone finds an AI out there that can generate good finite state machine diagrams. I've seen some that attempt it, but none that did all that well with the diagrams. So feel free to try that out. So. Let you work more on these prompts. And we'll talk a little bit more in a sec. So as far as scanning goes, one thing you'll probably see is sometimes AI will actually generate scanning or code for you. So like here AI is giving me Java code for a Lexer to tokenize Java code. So again, you'd feed in Java code, it would output a set of tokens here. So here's our different tokens it could output here. And then it actually builds this Lexer class. So if it starts seeing a number, it would process this and build, recognize the digits here. If it's seeing an identifier here and it has a tokenizer that looks for different symbols here, adds tokens to things. So it's actually giving code. Sometimes it'll give JavaScript code for doing this. Sometimes they give Java code. So if you like to see the code, these systems can actually give you, actually write code for tokenizing here. This actually, and we'll get into parsing. This can actually generate, does recursive descent parsing here also. So you have to decide if you want that. I don't find the code all that useful sometimes to understand it. So I'll often there'll be prompts in here to say, can you give me an example by how we do this by hand or something like that. So how we'd do this. So see when you're looking at this sort of approach, if you're getting code and if you like that code, or if you want the code in a different language, or if you want it, feel free to ask it to do it in without code, or to walk you through it by hand or something like that. Similar with parsing, this recursive descent. A lot of this, they can do this sort of stuff relatively quickly here. So, okay, so I'll just warn you that, yeah, you have to decide if you like to see the code or not with these. And then be quiet again. All right, why don't we just talk a little bit about parsing, and I think I'll wrap this up today and let you go through the rest of this without me. So again, remember, we're first doing scanning. And again, with scanning, we're taking, here's a Python statement. If X is greater than 10, tab, print, parenthesis, quote, large number, quote, parenthesis. So we break that into a set of tokens here. So if, and then we have if, and then this is the identifier. If identifier, this is a relational operator. And then this is a number. And this is a colon. And then we have our indent. And then we have a print statement here, which is an identifier here. We have a left paren, a string, a right paren, a new line, and a dedent. So again, we break it down. And then this, the tokens is what we really feed into our parser for this. Now, often we'll specify things like identifier X or string, and then what the string is as part of this also to help with this. As far as keywords go, like if and print and stuff like that, there's often a separate step we didn't talk about that substitutes all that, looks through all the identifiers, and if they're a keyword, we'll just switch them out to a keyword. There's not a good way to handle that usually in this stuff. Now, when you're parsing, there are a couple of techniques. I'm just going to show you, see if you understand the shift reduce parsing. And then in the exercise tomorrow, we'll talk more about recursive descent parsing here. And the shift reduce parsing kind of works with a stack here. So the idea is that we have our set of tokens here. Again, here's our sample expression in Java. And then we convert that to a set of tokens, and we start putting that in. Here's our new item we're dealing with, and here's our stack. So it starts off empty, and we push if on the stack, and then the left paren, and then an identifier, another here, and a relational operator, and then a number. And then once we have this identifier, relational operator, and number, we always look at the stack and see if there's a rule we can apply to reduce the rightmost part of the stack here, or the topmost part of the stack. And we have a identifier, relational operator, number rule up here, variable relational operator number. So we can replace that with just an expression here. So again, we'll pop off these parts of the stack and replace it with just an expression. So anytime we can apply a rule to the top part of the stack, we will. Now we have a left paren expression, we add in the right paren. Now we have left paren expression, right paren. And again, we know what that is. That's an expression. We have a rule for that. And then we'll pop that off and just put on an expression here. And then we get our brace and stuff. So again, it kind of pushes things off the stack. And every time we look at it, we look at the top of the stack and see, is there a rule that we can use to pop that stuff off and put a smaller item onto a stack with that? So, and then we end up with this parse tree here. And you can look at, again, we'll look at the other kind, which is called recursive descent. Now, how many of you, now, what is the course? Chris's course, the third Java course, data structures, where you do trees there. Are you doing, did you guys take that? Have you guys taken that already? Or is it after last semester? You last semester? Have you taken it yet? No, last semester, yeah. So again, there you probably learned that trees and like depth first search, or tree transversal, or breadth first tree transversal sort of stuff. And again, you'll see, again, you don't need to know that stuff for this, but if you kind of understand what depth first or breadth first, you might want to ask some questions if you know that, on how these methods, is the shift reduce parsing, is that a depth first search, or tree transversal? And again, this when we get to recursive descent, how you might want to look at how we process this tree, or how we create a tree based on that sort of stuff, how we parse it. So okay, so Thursday, we'll go through and try to do a little discussion on your QQSPs. Again, remember, we want a student prompt added in here for this. And we'll do a POGO activity on scanners here. I'll try to get I haven't finalized the assignment. I'll try to get the assignment up by Thursday also. Just a quick note. Next week, I'm going to be out of the country for the week. So I'll be online, but we won't be meeting in class next week. I'm thinking of not having a substitute. Well, I'll just post a lecture for this, and we'll just do it as an online class. We'll do the same sort of discussions and sort of stuff online. So next week, for the 2 class periods, we'll just do it online and asynchronously. Okay. So I'll post more details on that as we get closer. But I want to give you a heads up that we'll just have, as far as our high flex class, we'll flex that direction next week, asynchronous. Okay. Sounds good. I'm gonna Zoom people. Any questions here? Okay. I'm going to let you keep working on this. I'll keep the Zoom working, but I'll stop the sharing in case you come up with any questions, but we'll wrap up stuff and I'll shut down the screens here. So pause this.